And we are back again. I apologize for these very small breaks. It's just I underestimated the amount of awesome content that we're gonna have, and it's just I cannot miss this opportunity to ask questions while I have this chance. I think it's just an amazing opportunity. So I very much invite everyone else to join our Slack channel and ask your questions as well. So now we are gonna continue our summit with the Oleksandr Stashuk's talk on optimizing application binary size on mobile. Oleksandr?
Hello everyone, my name is Alexander and I work as a software engineer at Facebook. One of the things we care deeply are our mobile applications and making sure people around the world are able to access them. One important aspect of them is the size of the binary that is distributed to people, and today we are going to talk about it. First, we want to understand the reasoning why the application size is so important and why should we work to maintain and reduce it. Second, we'll analyze a bit what mobile app typically consists of and what are the files that we mainly ship. Finally, we'll look into sustainable ways on how we can slow down growth of the app as it is being developed by hundreds of developers, and what are the techniques that can be used in this space. We'll mostly talk about Android applications, though it is applicable to pretty much all of the mobile platforms. So first, why should we care about this problem? Large binary size is a significant obstacle for people installing the app in the first place. People need to download the binary over Wi-Fi or cell and potentially pay for it. Then the app would need to unpack and install itself and take even larger space on the phone, which might not be even possible on some of the disk-constrained devices. Google published a study in 2018 that 337 million smartphone users are there with limited data plans. In another study of them, for every 6 megabytes increase to the binary size, we see a decrease in the install conversion rate of 1%. We repeated such experiment and found surprisingly similar results. Our users would also notice performance issues when using large apps on mobile. In order for app to start, we need to load from disk significant amount of code and resources. On lower-end phones, that can take significant amount of time, and even though the code is typically memory mapped, there is still additional memory footprint increase, which might lead to reliability issues. Finally, when application is loaded, typically the code is executed, which uses the CPU cycles, which could be doing other important work on the critical path. As such, large app poses worse performance characteristics, and the less code you write, the better app you have. So what exactly is large in the mobile apps, Android in particular? Typically, most of it is present in the code, which can take two forms. Android Java bytecode, which is called DEX, standing for Dalvik Executable Code, and code coming from native libraries. They often occupy the largest chunk of the size. Resources and assets are typically images, sounds, layout definitions, styling that are bundled within the app. Finally, all of those files contain additional metadata. Every file in the binary needs to be signed, and every file name contains some archive metadata. Growth in the mobile application typically takes two forms. One form is the large, sharp increase whenever a new dependency or library is added. Most of the time it is easy to notice. More common though is a slow addition of multiple features which by itself are very small, but cumulatively they add a ton to the binary size, especially when 100 developers are working on the application. There are a lot of already existing approaches to pay attention to the first large increase problem, so we will tell a bit more what can we do towards the small features problem. So what can we do about it? Chasing every individual change and optimizing it seems a bit unrealistic. What can we be doing instead is focusing on our tooling and packaging and making sure that the code that we emit is optimal. We can also write our code more modular and use better frameworks. Finally, another approach is to build the attribution of the code to the organizations and introduce budgeting for every feature that we want to have in the app. Making sure the footprint of the code and resources for the given functionality is minimal is the biggest lever that one can have in the mobile apps. There are a bunch of tooling already existing which emits more compact code, most of which is open source. For example, Redux is the whole program code optimizer for Dalvik bytecode, producing significantly smaller binaries. We can similarly apply aggressive compiler optimizations like -OS, which for devices with slow disk I/O actually might perform better than -O2, as we need to read less code from the disk. Let's look in particular code example, taken from Redux open source portal. On image 1, we have an outer class alpha, along with the namesake private static field alpha. We also have an inner class beta, which has a method double alpha that uses outer static field. Unfortunately, due to the limitation of the bytecode opcodes, inner method double alpha doesn't know how to access the outer static field. As such, compiler generates additional access method, which we show on the image 2. This method simply gets the value of this field using opcode as get. Finally, on the image 3, we can see method double alpha implementation, which calls this generated access method. For the cases like that, Redux can remove this synthesized method and simply inline the necessary results for the callers. As such, we can make smaller code footprint. We additionally can use other optimizations, use better code layout using such tools. Additional improvement we can do is to compress and save our resources efficiently using PNG crash, WebP, or other techniques. To add to all of it, combining files together or minifying their names also improves size, as we have less smaller signatures and less metadata overhead. Let's look below at the context of typical binary called typical APK. We'd have entries in resource folder, which tells that there is some image for medium density screen, denoted by MDPI for right to left style, named spinner progress. We can teach our resource system instead to name it r/zv.png, and while the compressed content size will be exactly the same, zip entries overhead would be much smaller because the file size is smaller. Finally, every file is signed for security purposes in the binary, which contains file name and SHA-256 signature. Having smaller file name would make smaller signatures as well. Another angle to look into smaller footprint is better compression, which for Android apps by default is deflate. A full disclosure should be made that we simply can't pick the best compression in terms of byte savings. There are a number of trade-offs one should think of. Compression would require apps to decompress their contents, and first install after app upgrade would be slower, taking more CPU and RAM. Finally, app stores typically don't send the binary as a whole, but only a smaller delta difference, and we need to be careful to keep this contract. For example, Google Play Store, as much as known, would be sending a BS-diff delta. Once those trade-offs are known, we can explore improving deflate with 7-zip and omitting metadata using ZSTD or LZMA for assets. We are also looking into proprietary compression ideas which perform even better specifically for mobile bytecode and would hopefully be able to share more with community soon. We can also enforce certain code practices for better code, which is always easier said than done. For example, building modular code and enforcing the boundaries would make sure we don't take any unnecessary dependencies. we can use frameworks like Flutter or React Native that are providing more dense and compact code at potentially expense of some of the native features or performance. Finally, approach would be moving most of the business logic to the server while making the clients only render the content. The approach that is typically taken by the light apps. You can see an approximate chart of growth for typical mobile app colored by green and another light app by blue. The more developers and features are there, the faster the green binary size grows. Instead, for the light apps, denoted by blue line, they are typically keeping their size close to constant and only have small increases when a new piece of infrastructure is added to support the given product functionality. All of this might not be enough. For large apps like Facebook, where we have hundreds of developers, we can consider introducing quotas or budgets for every individual feature like feed, notifications, marketplace, and so on. If the team goes significantly beyond their quota in a given time frame, say a week or a month, it is forced to clean up their code and make sure that the footprint stays at a similar level. And that is it for the talk. Hopefully it was useful for people to understand the needs of the binary size for mobile applications, and you got some tips on how to improve it. Let us know if you have questions.
Awesome. Thank you so much, Oleksandr. It's for this overview of the techniques that we can use to reduce our binary size. Let me check if we, looks like we currently don't, since we currently don't have any questions, I can ask my questions. So in a lot of the points that you brought up, you mentioned that, for example, it's pretty hard to do a static decision. Like, for example, when we decide which compression algorithm to use, or when we decide even things like which compiler flag to use, because obviously there are, like, for example, in Clang there is OZ, which is optimized for size, but there are also a ton of other parameters like inlining size and all sorts of other parameters that affect the final size of the binary. And making these decisions statically doesn't necessarily make a whole lot of sense just because you don't know in advance what's going to be the optimal configuration. So I'm curious if you have tried any of the techniques that are, I guess, in some way at least similar to what Eiko was talking about the optimizing these systems dynamically or automatically.
So unfortunately, we are really bound to the distribution channels for the mobile application. It would be so nice, to actually try on the fly, especially with the binary, all kinds of different optimization. But the way we ship our binary, we typically go through the Play Store or other app stores, and then based on the rules that are set in there, we really want to have one. Another problem related to it is that mobile applications are really hard to get upgraded. So whenever a new version comes up, you want to make sure that all of the people are getting it. And if you put, some of the users in a bad state, they can stay for there forever and we can lose them. So with all that in mind, it's way harder to tune things in the mobile world. And while we can try, realistically, it's way more harder.
I see. Well, actually, we unfortunately are out of time, but fortunately, you're going to be on the panel that we're going to have later on, I believe. So hopefully we'll have a chance to continue this discussion in even a broader setting, because I actually believe that there is a lot of potential, and maybe distribution channels, if they want to leverage some of these dynamic optimization techniques, they can actually perform some of these optimizations automatically. That's actually the reasoning why, for example, Apple was insisting on everyone submitting their bytecode instead of just the compiled binary, because it makes it a lot easier for them to run extra tools and optimization techniques to produce the binary that fits the bill the best. And I believe Google actually already started applying some of these techniques for ahead of time compilation, where they can use profile information to decide on some of the techniques before the app is even shipped to the client. So I just hope that these are the techniques that are going to be combined and deliver magical experience and like tons of awesome optimizations for free. So yeah, thank you so much again. I'm looking forward to seeing you participate in the panel. I'm very sorry that it looks like it's very dark outside, so I assume that you're based in US, which is very, very unfortunate. But I really appreciate you taking this time and surviving all like, you know, spending this night with us. Thank you so much again, and see you again. As for everyone else, we are gonna transition into the best part of the summit, which is obviously the lunchtime, and hopefully the hour dedicated to it will be enough for you. So I'm looking forward to seeing all of you back at 13:25. And the afternoon session is going to be kickstarted by the Mikhail Bezios, who's going to talk about optimizing application performance by automating the data structure selection and tuning process, which again goes into the same, like it continues the same topic of, you know, how can we get magical improvements by default? That's the whole point of using common infrastructure. And as our systems grow in complexity, it really helps to have systems that not only come up with the best possible configurations and algorithms for us, but also keep maintaining all these characteristics as time progresses. So enjoy your lunchtime, and I will hopefully see all of you and even more in 1 hour. Thank you so much again.